In soundbite video number 32, entitled, "What is the most important location in a turntable?" I proposed what I believe is the right answer to the question, which happens to be the pivot point of the cantilever in the cartridge. Because, as I stated in that video, we want that location to remain immeasurably still in order to maintain optimal faithfulness with the groove content. In today's video, I want to expand upon that concept and share with you some data. So it may help for you to refresh your memory to go back and watch that video number 32, and then the rest of this may make a little more sense to you. In our development and research on the Colossus headshell for Kuzma tone arms, we took this idea very seriously of ensuring we could do whatever we could possibly do in order to have this location in the cartridge, this pivot point of the cantilever, remain immeasurably still. And we spent many days measuring under different conditions the acceleration of the headshell versus a standard Kuzma headshell while playing various different test tracks. The output of one of those tests is found on the Colossus webpage on our website, and you'll see a comparison of how much acceleration was measured on a horizontal plane at the headshell when playing a pink noise from 20 hertz to 20,000 hertz. And we were measuring the response from 10 hertz all the way up to 10 kilohertz. You can see very clearly that there's a dramatic reduction in acceleration of the headshell for the Colossus versus the Kuzma. It's quite dramatic when you look at this graph, how much less the Colossus headshell gets displaced by the groove content versus the Kuzma headshell. And this is the case throughout the frequency spectrum. But let's dive into these results a little bit further. First thing I would have you note is that at about 100 hertz, you'll see a big spike for both the Colossus and the Kuzma. This is the turntable's rumble. There was no getting around this. The accelerometer was measuring it no matter what test track we were playing, and that amplitude stayed pretty much the same across every test track that we played. So we'll have to look elsewhere on the graph for the Colossus's beneficial impact to this picture. You see a lot of the peak energy exhibited by the Kuzma headshell was reduced both in amplitude and in frequency. Now that's a function of the extra mass and extra volume, the reason why both of those things were happening. But let's remember, this is rigid mass, and the solution isn't just to add mass. It must be rigid. If you look on the part of the graph at about 2,500 hertz and above, you'll see a real dramatic reduction in acceleration for the Colossus versus the Kuzma. Here's another graph. This is showing acceleration when measured on the Kuzma headshell and separately the Colossus headshell when playing a test track that's a purely unmodulated test track. There's no content in the groove. We're just playing a silent groove. Again, you can see the 100 hertz rumble that's coming from the turntable itself, but you can still see that the Colossus has got a significantly lower noise floor than the Kuzma headshell. You'll notice on this graph that the Colossus traces have a number of very narrow spikes. This is actually electrical noise that we were having difficulty tamping down. We're still figuring out how to reduce this electrical noise. But so a lot of these very narrow spikes in this region here, they aren't even a measurement of acceleration at all. That's just the electrical noise floor of our system. If we turn our attention to playing square waves, whether it's 500 hertz or 370 hertz, you see the same picture. When we've got greater rigid mass, we get a lower noise floor. There is less acceleration, that unwanted acceleration going on at the headshell. you'll see again that not only does the noise floor decrease, but the peaks of the harmonic resonances, they decrease as well. These are the type of results you want if your goal is to optimize vinyl playback. What we're seeing here is a picture of the tail wagging the dog. And that's not what we want. We do not want groove content to be modulating the position of the head shell. This is, by definition, will be mechanical noise, and therefore it will become electrical noise and it'll become part of your noise floor. It's the type of thing that you don't know even exists until you've removed it. And then you get to experience all of the typical benefits, the extra resolution, the better transient impact, better separation of instruments, the larger sound stage, the longer instrumental decay, and so forth. This is what it sounds like to lower your mechanical noise floor. This is accomplished through the proper use of higher mass and high rigidity, but the devil is always in the details. There are ways to screw that up. There are a number of ways to screw that up, and actually the matter gets rather complex when we start talking about mechanical impedances and energy propagation through non-uniform bodies. Anyway, subject that is unlikely to be the topic of just a 5-minute video. Okay, so there's a little bit deeper dive into the results of our recent measurements. Again, as I've said before, I'll be talking much more about rigidity and mass in future videos and blog articles. So until next week on the next soundbite, see you there.